We're into chapter 8 now, where we're going to discuss rotational motion. To start, I want to remind you of some common terms when dealing with circles. If you connect one side of a circle straight across to the other, that's a diameter. I'm going to represent it with the letter D. If you connect the midpoint to any outside point, that's called a radius, and I'll use a lowercase r for that. The diameter and the radius are related, where the diameter is just 2 times the radius. If I look at this outside here, which I'm showing in blue now, the distance all the way around the circle is known as the circumference, and it's related to the radius as 2 pi times the radius, as the circumference distance. Pi is that mathematical symbol. It's just a number. It's roughly 3.14. All right, let's look at this point right here now, specifically. If I can draw a line that has basically the same shape of the circle at that point, like this, that's what we call a tangent line. In mathy terms, it has the same slope as the circle at that point. I'm going to connect that dot with the radial line, and the tangent has the relationship to the radius there, as a tangent line is always perpendicular to the radius for a circle. So we could draw this combination at any point, and they'll always have this property. Perpendicular in this case is referring to a 90-degree angle between the tangent line and the radial line. Right, now we're ready to get into a specific type of rotational motion called uniform circular motion. So circular motion is kind of obvious. It's just any time you're moving in a circle. And we're going to consider perfect circles for this course. Uniform is a special case of circular motion when you're moving with a constant speed. Here is a simulation of a ladybug moving in a circle with constant speed, so we'd call this uniform circular motion. The thing I want to point out is the speed we said is constant, but is the velocity constant? Remember that velocity cares about direction and speed, so I can show that velocity here. And the answer is no, the velocity is not constant because it's continually pointing in a different direction. However, it's always pointing tangent to the circle. If you remember my definition of a tangent line, it's always tangent. The length isn't changing because that's representative of the speed. As I mentioned, it's constant speed. So here's a diagram of that ladybug's motion. So as I mentioned, the velocity is not constant because the direction is always changing. However, it is always tangent to that circle at every point. We're actually going to focus more on the speed than the velocity in this chapter, so we can call this the tangential speed. If you remember from previous chapters, we often use the word linear speed, and that's when you're moving in a straight line. This clearly isn't a straight line, so we don't use the term linear speed in this case. All right, so imagine this is a particle and it's just moving around like this. Notice that its speed is constant, and because it's a circle, we call it uniform circular motion. But the fact that it's constant speed is actually quite important. If you remember from earlier in the semester, I said that if you have constant speed, then you can define the speed as simply the distance traveled divided by the time it took to travel that distance. So let's play the motion again, but this time let's pretend like we're tracking the time. That's easy enough to do with a stopwatch, and we'll pay attention to the distance it's traveling during that time. Okay, so I recorded the time, and the distance was just that right there. So we could measure that easy enough. So from that, we have the distance traveled and the time it traveled that in. But since all of this motion is tangent to the circle, what we found is just the tangential speed for our particle. So if you'll notice tangential speed, it's the same units as just regular speed, just distance over time. So meters per second or miles per hour. I want to look at the motion a little bit different at this time. So I've drawn a radial line, connected it to my particle so that when it moves, it's going to move with that radial line. Just watch the motion a little more carefully this time. I don't know if you happen to notice, but it made 2.5 rotations during that time. Another way to represent the motion is to simply define the number of rotations and divide that by the time it took to make those rotations. If you do that, it's known as the rotational speed. Okay, so a common device that uses rotational speed that you would recognize is one of these things. This is called a tachometer. So if you notice right there, it's labeled RPM, and you probably know that RPM stands for rotations per minute. Now this per, I've said this before, this is just a division operator. So we can really write that as rotations divided by minutes. Right, well, that's just what we have up here. So number of rotations divided by time, rotations divided by time. So RPM is one way to express rotational speed. So we could call that a unit of rotational speed. You might have also heard RPM as revolutions per minute, and that's fine. In this case, they're really saying the same thing. So now we have two different ways of describing the motion. We have tangential speed as distance over time and rotational speed as number of rotations per time. So here I've marked two different particles. I'm going to have these move around, and I want you to consider this to be a solid disk. So think of these as two smudges on a spinning DVD or two bugs on a turntable, however that works. Right, as they move, I want you to consider this question. Did they have the same tangential speed? Well, let's just watch. Okay, so they did both have constant speed, but did they have the same tangential speed? Well, it's just a question of this. Did they have the same time, and did they travel the same distance during that time? Well, the time, yes, for sure. They were moving together, so the time is the same. So it's just a question of, did they travel the same distance? Well, the outside one here was traveling all the way around the circle, what we'd call the outer circumference. The inner one was following a circumference like that. Okay, and it's clear that this inner circumference is a lot smaller in total difference than the outer one. So the answer would definitely be no. They had the same travel time, but different distances. Okay, we're going to modify that question a little bit then. Which one had the greatest tangential speed? Now let's just watch. Without the bar connecting them, it's a little more obvious that the outside one definitely had the faster speed. It had to travel much further in the same amount of time. So you can definitely say the outside particle had the greatest tangential speed. All right, last question. Did they have the same rotational speed? Watch this time. Well, if you were noticing, they traveled exactly 1.5 rotations, and it was the same amount of time. So rotational speed is number of rotations per time. So in that case, yes, they had the same rotational speed because same number of rotations in the same amount of time. Rotational speed is often identified with this symbol. It looks like a W, but it's actually not. It's the Greek letter omega. And that's just a symbol we give to easily identify rotational speed. Tangential speed, v is common for speed, and I just put a little subscript there of t to identify it as tangential speed. So what I've tried to show with these questions I've been asking, first, for a solid disk, all points will have the same omega, or in other words, the same rotational speed. That's true of all solid rotating objects. However, we did find that not all tangential speeds are the same for every point. There's a relationship that connects these two and highlights the difference in the tangential speeds, like this. So the tangential speed is equal to the rotational speed multiplied by the radius. So this is the same for every point. What distinguishes the tangential speed is then just the radial distance, or how far it is from the center. So for this inner particle, that's its radius. So it's noticeably smaller than the outer particle, which has the longer radius. So that's how you can distinguish between tangential speeds. So we can say then that points farther from the center will have greater tangential speeds. So I'm sure you're wondering at this point, why do I care about any of this? Well, there are lots of practical applications. I'll just show you a couple of quick, obvious ones. For the first one, I'm actually going to use a can of chili, and I'm just going to roll it across the table like this. So if you notice, that can rolled pretty much straight when I pushed it. Now I've got just a plastic cup, and I'm going to try to roll that straight across the table. Clearly there was a noticeable difference there. The curved path of the cup is obvious when you compare the shapes. So the chili can, the top and the bottom of the can have basically the same diameter for its circle. The plastic cup, however, from this perspective, I think it's pretty clear that the top has a wider circular pattern than the bottom. Okay, what I did was I actually traced out the top and the bottom, and it's an obvious difference. If we apply what we just learned, because this cup is a solid cylinder, every point will have the same rotational speed. So the top and the bottom will have that same rotational speed, meaning same revolutions per minute. Because the top and the bottom have different radii, though, they don't have the same tangential speed. So the top has a higher tangential speed because of the wider radius. And so when it's rolling, it must cover more distance in the same amount of time. Well, the only way it can do that is to follow a curved path. So let's look at that again. I've sort of traced out the motion. All right, if we compare the starting points here, this yellow line, this distance is less than this outer distance. So that's the only option the cup has because its top has to cover more speed than its bottom, so it's a natural curve. An application of this, the book discusses this, and I'll let you read that. It talks about how train carts that follow railroad tracks will have this tapered end, which helps them keep stable. And you can read about that in the book a little more. To me, an interesting application is this. Hopefully at some point in your life, you've driven down a road kind of like this. And what I want to highlight is actually the rough edge over here. So this is loose gravel, just not far from this white line. So if you've ever had this experience where you're driving on a road like this, and you swerve just a little bit too much to where one side of the car catches that loose gravel, you've probably felt that panic of the car suddenly jerking to the right. Have you ever wondered why it does that? Well, the answer is just rotational motion. So when the right side tires hit that loose gravel, they slow down because there's a lot more resistance with that loose gravel. But the left side tires are still going at that original speed, so they're going faster. So now you have one side of the car that has slower tangential speed compared to the other, So it's like the cup. It naturally tends to curve for its motion. I've always thought this is an interesting application of rotational motion. If this ever happens to you again, I hope after you safely get back on the road that you'll think back to this moment and realize, hey, I know why this happens now. We're going to shift gears here for the second half of this video. This might be a good spot to pause and take a break if you want to. Hopefully you watched the videos that I posted on the first day of the semester. If you did, then you'll remember this demonstration. We had a race between two objects, a solid disk and a ring. We raced them down this ramp, and I claimed that they had the same mass and the same diameter, and I wanted to know which object will win the race. Do you remember which one won? Well, if you don't, we can just watch that video again real quick. We looked at it several times and used different configurations for the starting point. And in every case, the solid disk won. And I claimed at the time that the solid disk won because it has less rotational inertia. Well, we're now at a point that we can really explore that concept of rotational inertia. Remember that inertia in general was a property that describes an object's resistance to changes in motion. Rotational inertia is just a slight modification of that. It's a property that describes an object's resistance to changes in rotation. So it's really only one word different. So inertia is just motion in general. That's like left, right, up, down, diagonal. You know, anything where the object as a whole is changing its position. With rotational inertia, the object doesn't actually have to go anywhere. It just has to be rotating. So if it's standing in the same spot, but it's spinning, then that would be a description in which we would want to consider rotational inertia. The key to both of these concepts is the word changes. That's really what should jump out at you if you ever think of inertia or rotational inertia. As an example, here I have a solid disk and it's moving with uniform circular motion, which means that it has a constant speed. Well, the constant speed means that its rotation is not changing. So what we can say then is because there is no change in its rotation, the rotational inertia is not really of any interest. It's not going to be any prime factor for our discussion. Rotation itself isn't the concern for rotational inertia. It's all about if the rotation is changing. So remember that word, changing. That's the key word. So in the case of our race, the rotation of the objects was changing. So that's why rotational inertia was a primary factor in determining which object won. Again, rotational inertia is a measure of an object's resistance to change in rotation. The solid disk had less rotational inertia than the ring, which means there was less resistance to change. So in other words, it was able to spin up faster or accelerate down the hill at a faster rate. So that's why it won. So we need to define which factors are the primary influences on rotational inertia. The first should be fairly obvious. Mass is a primary consideration. So the more total mass you have, the more rotational inertia you'll have, meaning more resistance to changes in rotation with more mass. The second factor is the one that really distinguishes rotational inertia from regular inertia. So that is how the mass is distributed around the rotation axis. So if you move your mass further away from the rotation axis, the rotational inertia increases. And then reverse of that, if you gather more mass closer to your rotation axis, the rotational inertia decreases, meaning there's less resistance to changes in rotation. Here's an example. I have two solid disks, and their total masses are the same. The red dots here just represent extra masses that I've set on top. So think of this as like a turntable with 2 extra weights sitting on top. And these are just 2 different configurations. Okay, the rotation of these is about the center, so about that X point, so kind of like this. Let's say we want to change the rotation of the bottom one. So that's what I mean, that it's going to rotate about its center. The question I have for you then is, which disk has the greatest rotational inertia? Well, let's go through our 2 primary factors. First was mass, but these have the same total mass, so that can't distinguish between the 2 of them. So the second factor was how the mass is distributed, and the bottom one has mass that's located further away from the rotational axis than the top one, so definitely the bottom one has the greatest rotational inertia. All right, now here I've made a slight change. The objects themselves are the same, but now I'm going to rotate them about this point. These X marks their axis of rotation. So it would look something like this. Okay, in that situation, which disk has the greatest rotational inertia? This time, the bottom disk has the mass located closer to the rotation axis, where the top one, the mass is located further away. So the top disk now has the greatest rotational inertia. So the key I'm trying to emphasize with this is that rotational inertia changes with a different rotation axis. So it's a much more complicated concept than just regular inertia. Regular inertia is essentially just mass. Rotational inertia is different in that it's not just a mass issue. I mean, yes, that's part of it, but it also depends on how it's distributed. So density comes into play with rotational inertia. If the density is not uniform and some areas are more dense than others, it's really going to affect the overall rotational inertia. Here's a table of some common shapes. So every object has a rotational inertia depending on how you rotate it. These are just some common ones. All right, so m on all of these is the mass of the object. For these rectangular shapes, L is just the long axis length. For our cylinders and spheres over here, m again is mass, but r is the radius. So the reason why I like this column over here is because every term has mr squared in all of them. So if we assume all of these objects had the same mass and the same radius, then the key to determining which one has the greater rotational inertia is just this factor, this fraction out front. So you can see that the biggest coefficient out front is 1. So the cylindrical hoop, if all of these 4 had the same mass and radius, the cylindrical hoop has the greatest rotational inertia. So it will have the smallest acceleration, and that's why it's going to lose the race. The solid disk has half of the rotational inertia as the hoop, so it could accelerate twice as fast. Now what's interesting is what if we had raced a solid sphere with these 3? Well, 2/5 is actually less than 1/2, so in that case the sphere would have won. This would have still been last place. And then if we'd raced something like a basketball that has a hollow shell inside, but assuming it was the same mass and radius, 2/3 is greater than 1/2, but it's less than 1. So ranking wise, you would have this one be first, then the solid disk, then the spherical shell, and then the cylindrical hoop. I hope that is making sense. Now, over here on the left, I really like how this is showing that even if you take the same object, so same mass and same length, and you just rotate it about 2 different points, your rotational inertia changes. So 1/12 is much smaller than 1/3, So if you rotate a rectangular stick like this about its center, it should be a lot easier than if you rotate it about the end. There's a simple demonstration of this. You can try it at home. Here I have a broom handle. I'm holding it at the center, which means that's its rotation axis. And I'm just going to change its rotation. Notice that means I'm just wiggling it back and forth. So our discussion of rotational inertia says that if I now hold it at the end, so this end is now my rotation axis, that should give me a higher rotational inertia, which means it should be harder to change the rotation. Let's watch that. It's not so obvious from the video, so I really recommend you just try this at home. Any stick will work, but it was significantly harder to wiggle it around holding it at the end than it was at the center. And if you couldn't see that from the video, just try it at home. It's instantly noticeable when you try it for yourself. Here's another application. You've probably at some point seen a tightrope walker or an image or video of one. I like this picture because it shows the old-timey circus outfit. Oftentimes you'll see them carrying a long pole, and have you ever wondered why they carry that long pole? Well, most people say because it helps with their balance, and that's true, but it doesn't really explain the physics necessarily. Well, now we can actually explain the physics. What the pole does is it increases their rotational inertia, which means they now have more resistance to changes in their rotation. And remember that word changes is the key. So they're less likely to start changing rotation, which in their case means tip over and fall off. As one last example, if you're a baseball fan, you might recognize this person. This is Hank Aaron. And the way he's holding the bat right now, notice how he's gripping it at a higher location on the handle than you might normally think. This is referred to as choking up. By holding the bat higher, the rotation point is now right here. And so more of the mass is closer to that rotation point than if you hold it down here. That means it's going to have a lower rotational inertia, which means it's easier to swing when you make your swing. That's not always a good thing though. Notice in this other picture he's holding it lower, and I'm guessing this is how he actually hits in a real game. It's harder to swing this way because your rotation point is down here and now more mass is further away, so higher rotational inertia. But it also has the advantage of the longer radial distance means you have a higher tangential speed when you actually connect with the ball. So that's going to create more change of momentum for that ball, and thus you should be able to hit it harder. So it is harder to swing that way, but it's also supposed to give you a better hit. There's actually more physics principles that we could bring in that would help explain this, but we'll just stick with those two for now because those are what we're covering right now. Let's take a break and end here. In the remaining videos for Chapter 8, we'll cover concepts like torque, center of mass, and angular momentum.